Thanks, everybody. Apologies, I have a bad cold, so I might pause, so excuse me for that. I just want to get a perspective on how many of you have sort of heard of serverless or familiar with the concept of serverless. That's great. Yeah, I'll just try and level set in the first 5 minutes, and then we can get into the meaty architecture and the machine learning aspects. Microservices, when we talk about microservices architecture, you sort of want to decompose your service into really these small constructs and execution units. And this sort of blends really nicely into building function as a service. So each microservice, depending upon how contained you want it to be, blends itself really nicely into function as a service. So that's what essentially Lambda or serverless becomes, which is this function as a service, where your execution unit you decompose into a function that responds to an event. So when you think about events can be different in, it could be changes in data, right? You happen to store some data, that is you put data into your data store, or the data gets modified, the data gets deleted. So you can think about these as events. But these can be events as events into request to an endpoint. Especially, let's say, if you have an HTTP interface, that could be an event as well. Changes in any resource state, maybe somebody accessed a database or a certain event in your monitoring system. Are you okay? All right. So we then can define a package of function along, so we provide AWS Lambda provides a runtime environment for execution in different languages, so Node.js, Python, Java, C#, and Go. So you have an event, you have a function that consumes that event, you get metadata on what that event is, and then you respond. And then you basically have access, depending upon your access policy, to do anything you wish. So in the AWS ecosystem, you could be writing to an object store like S3 or a database, or just respond, give a JSON response after processing. So there's an inherent thing here, which is because you're running function as a service, your time is sort of limited. That's one of the aspects. So you have you can set a timeout threshold. The maximum sort of happens to be currently at 15 minutes. But there's also, what about the compute unit? So the way we sort of define the compute units are mostly in terms of the memory that's provisioned to you. So, for example, you can have a max of 3 gigs of memory, but you could have a 128 meg memory for a small function. So you have the flexibility to choose what fits the best profile for the function you're trying to execute. So why is this pretty attractive? So it's really nice when you think about functions are the unit of deployment, right? From a test perspective, from an operational perspective, you're looking at this really one small piece of execution unit, and it scales per request. Now the good thing about once you deploy your function, you're not necessarily trying to, okay, how do I go from a single request to a million requests? You're not operationally thinking about that. More importantly, one of the most attractive thing is you never pay for idle. That is, you're not provisioning anything that you don't need to. The function spins up, and you execute when there is a request, and you don't pay when there is no request. what it does is it sort of abstracts away the infrastructure aspect, and you get to focus on the cool stuff. But I think one of the main things to think about in developing architecture patterns here is Lambda is stateless. So that's the single biggest thing you want to think about when you architect. So there's no affinity to compute. There is no affinity to any infrastructure there. There is a file system that you get, which is only 512 megs. But there's a key aspect there. Even though we say that it's stateless, as you can see, there might be a startup penalty that you pay when you spin up. So to sort of avoid that, what we do is we freeze your container, your Lambda container, and so that we can enable reuse. So if you send enough requests, your code is already there. You don't pay that penalty of that container spin up. So I really want to quickly go through some monitoring support, and then we'll get into the architecture aspects. So there's a distributed tracing service called X-Ray, and this is integrated very well into Lambda and other services. So you can instrument the X-Ray SDK, and for example, you can go all the way from user to what happened, how much time was spent on the Lambda execution, what was the time taken on your object store, read, write, etc. And you can get nice timelines as well to sort of debug and trace where your application is spending time. Okay, let's come to architectural patterns. So you could use this as an API backend, right? Like you think about, you set up your web server, you have your API endpoints, you can think of your CRUD application. You could totally use this, and a lot of people successfully build API backends. And what we've seen is people typically, talk about over 90% savings than, actually having a web server. And, a lot of that has to do with the access patterns that we see in terms of your requests, right? Like you don't have a lot of night traffic. You don't have, traffic is only high during a certain period of time. So for very spiky or bursty traffic patterns, you see this nice smoothing curve because it only spins up when you have a request. You could build producer-consumer applications. People build scrapers, image processing, video processing, all that. You could do ETL. You could read from streams and process the data. You could actually even do MapReduce. So let's talk about how we can build that scalable architecture to do big data processing. So I'm just going to walk through. So essentially, you have a driver function where you can configure what are the keys. Basically, you want to get the data, and then you build your functions to essentially have your mapper and reducer functions defined. And then what this does is it maps each of that to the data that you've given, writes the intermediate data to S3, and the orchestration is done by another Lambda function here that's listening to the mappers that have written to S3. And then once that's done, once all the mappers are finished, you can now take those intermediate data and process them or run the reducer, and finally have the output in S3. I'm going to walk through this with a little more it's probably easier to follow. So there are essentially three sets of Lambda functions here: the mapper lambdas and the reducer lambdas. The coordinator you don't need to write. It's really easy when you think about it, that you get the flexibility of writing what your mapper and reducer in a very simplistic framework. But also what's good is each part is isolated. right? You have a single data source that's an S3, and then it doesn't matter how many people are actually accessing it. So from a provisioning perspective, and sandboxing becomes easy. You don't need to provision extra resources, and people can access on the same data. So we'll go through the steps again. So the map phase, you know, maps to a bunch of keys, produces intermediate results, and the coordinator, once the mappers are finished, it needn't be. It's just simpler the way from an implementation perspective, which is why I have it that way. And the reducer then reduces recursively until you have a single output. By the way, this is open source. The code's available on GitHub. And there's a bunch of benchmarks as well on how it does compared to Hive and other open source solutions out there. Let's actually deal with a real use case here. So VPC flow logs. So these are network traffic flow logs, and common use cases you're trying to debug, or hey, I want to understand where network's flowing from, which Ethernet IDs, X1 and Y1. Let me get a complete list of what the traffic looks like. So this is a job that I'm running, and so it's actually about 420 gigs of data, VPC flow logs, and we're just trying to generate this one dictionary or JSON data where it's basically mapping Ethernet ID X to Y, and what are the bytes that have been transferred. And what's great is, if you look, we've mapped it to 213 mappers. So, in an instant, we can actually spin up these containers or Lambda functions, and because they're spread, as long as you're not looking for applications that are running 1 second. Right, like the spin up time gets amortized over the runtime, and there's slight variability, but not too much, as you can see, between each of these Lambda functions. But especially in this case, you still have to wait for the laggard, right, which isn't any different from other data processing frameworks. I'll try and speed up this a little bit. And then once the mappers are done, you can see we go to the reducer state, and as you can see, it actually spits out all the stats. So let's just analyze the stats a little bit. What you saw there was almost 425 gigs of data being processed, a total of 4,200 files. And total lines, that's 3.5 billion lines, and it ran in under 200 seconds and took us 52 cents to process all of that data. So it's pretty, from a cost and time perspective, it gets pretty attractive to do that. So next, I sort of want to talk about, it's not just about data processing, right? Like we want to get analytics, but we want to get predictive once we have analytics. That's how can we do that in the same pipeline? Which is why the likes of Spark or they're pretty attractive, because you have an end-to-end pipeline, and I want to see if can we do that here as well, right? MapReduce as a paradigm is generic. We can build a lot of different workflows on it. So let's take k-means as an example. K-means clustering, so we're trying to actually cluster things that are similar, and pretty useful when you think about operational. We might want to have, from a log perspective, we want to see where the hotspots are. So clustering could be very useful, or error codes. So we can apply this program essentially to those use cases. So this is just the pseudocode, and then I just ran this on a news event data set to sort of say where are the hot events happening all over the world, and as you can guess, like these days, a little bit of social media activity shifts, news centers pretty easily. So that's about basic or classical machine learning algorithms. So I wanted to talk a little bit about the more prominent neural networks that people use these days. From an architecture perspective, we can think about there's the training aspect, training your model, and then using your model. Training your model, we're still limited by the 15 minutes, right? Architecturally, if we think, hey, it's pretty cool that we can get almost unlimited parallelism, right? When you think about spinning 1,000 Lambda functions seems to be trivial than, say, spinning 1,000 VMs or containers. It's really easy to do so. It's just an API call away. Now, we could either do data parallelism or model parallelism. Now, data parallelism is where we split, chunks of data, and then there are copies of the model, the same model, and we send it through data, and then we can reconcile, like, hey, what is it that we've seen? We can exchange the weights, and then finally have a unified view of what the best weights for the model are. I'm just simplifying this for explaining the architecture. Now, model parallel is we can split each of the model into different parts, send the data, train the layers independently, and then sort of stitch them together. But the problem here is we can't get around the time limit, right? Like that's fixed. But hey, from a prediction or inference perspective, 15 minutes is way too long. We don't want things taking that. There's a lot of cases where we want instant results. So can we actually leverage Lambda here for predictions? The answer is yes. So there are a couple of projects I've built for ImageNet and Keras. There's one that exists for TensorFlow. So you can use these packages to actually run trained models, and we'll go through some benchmarks here to see how viable they are. So I basically hosted a LISA18 model, which is this is a image. It tells you, given an image, what is the image, what is in the image. Basically, an object classifier. And the model was hosted in Oregon, and I wanted to see what the global latency was across, and it was pretty viable when you think about the average latency about 1.18 seconds in terms of prediction, and this was about around 20% if you had actually hosted this on a standalone server. And what happens is the cost, as I said, gets amortized in terms of the spin-up time. Let's go a little deeper into that from a cost perspective. So as I said, the memory container, right? Like I could use, while my max is 3 gigs, I don't necessarily need that 3 gig data or 3 gig memory. So let's look at what the prediction time, the latency, and the cost goes as we increase the memory. So what happens in Lambda is essentially when you reserve more chunk of the memory, you basically get more compute time on the particular core. So as you can see, the prediction time sort of exponentially decreases as we increase the amount of memory that we give. But if you sort of look at the cost aspect, so there are 2 different models here, just to sort of show the difference. The left one, SqueezeNet, is a much smaller model, or a shallower model, and the ResNet is a more sophisticated, lot more layers, so more compute intensive on the right-hand side. The cost pattern looks pretty similar. So, you know, what essentially this is it's good to benchmark your application to find, you might not want to go all the way to 3 gigs or, actually when this paper was set, you know, the limit was only at 1.5 gigs, which is why you don't see the 3 gig limit in this paper. But the sort of takeaway here is benchmarking helps. You might find that sweet spot where the cost latency trade-off may be the best. But how did we actually achieve this, right? You know, we talked about Lambda being stateless, all this, well, it's frozen. You know, how do we not load the model each time? What's actually cool is you get a event hook, essentially. In this case, it's, say, Lambda underscore handler. So this is sort of your main function. So anything outside of this main function has global scope. So as long as you load things outside of that, you get to reuse that inside your function without having to load them. So these are your global or your static variables. So that's the magic, is you want to pay the penalty of loading the model once because that takes time, but outside the context handler, and then handle all events inside of that. What about more sophisticated projects? So there are a couple of projects up there. The first 2 are from UC Berkeley, where they've been able to run, so Pyran is a more, just a Python execution environment at scale. You can map any function and run them. The next is NumPy-Ren, so a linear algebra processing, where, you know, they've actually shown you can get, you know, easily at peak 5 to 7 teraflops that you can run pretty easily. Both of these are, again, open source projects, so I encourage, if you're into HPC computing, to try these. But also, you can actually run Apache Spark on Lambda. So Kubo has a blog post on this. What they've done is essentially replace the Spark executors by Lambda. So you still have a central sort of coordinator or an actual EC2 server, but then the actual executor units are Lambda functions. Clearly there's a pattern here, right? So what is that pattern? We want to store the data in S3, right? We have a central store, and the idea is we send compute to where the data is, right? The data is close to S3. You don't pay for the data transfer between the Lambda functions and the data in S3. You can get really high, if they're in the same data center, you're using the AWS backbone and not doing anything via the internet. And then what we can do is use S3 as a scratch space, right? You can use that as a scratch space, but also you can use that for inter-process communication. So that becomes your backbone in terms of your communication backbone channel. And then finally you can, store the results and, put them in a database or send them as a result, JSON result. Let's talk a little bit about CI/CD and productionizing this. We have AWS SAM, which is Serverless Application Model. It's templatized way of spinning up your Lambda functions. So again, this is open source, so feel free to use this. We actually have a serverless application repository, so a lot of the applications that I talked about are actually available on our website. You can just clone that and spin up your application. So it's pretty easy to get started. Just want to talk about more advanced CI/CD pipelines here. So things to consider, right? Like, where do your model artifacts live? So again, S3, as you go more advanced, you will have different versions of your model, and you're trying to understand where and how, which is the best one. And oftentimes, it's really hard to sort of do that without explicit feedback. Performance and latency is key, but we also need a strategy to roll out. Ground truthing is key, because some of these models are so objective. Let's say you have a model to increase your sales or your marketing spend, but you really don't know. You need to have a good way of mapping what's happened. So A/B testing is great, but make sure you home in on what that metric of success is. A/B testing, yeah, good, but truly it'd be great to sort of think about a MultiArm Bandit strategy. A/B testing may not be sufficient all the time, so you want to have more different models. You want to think about a more sophisticated way, a staggered way of releases, just like you think about in other applications. So MultiArm Bandit, I'll quickly summarize this as there are two constructs here on explore and exploit. So when you explore is you're trying to find which is the best model. Once you find what's the best model, you want to exploit, that is send maximum traffic to that. So here's how you could do MultiArm Bandit, more like 2-arm Bandit just for now. But the idea here is you don't want to just fix a percentage. You want to dynamically understand the metrics that are flowing in and being able to sort of change, right? Like maybe as you go through a new model, you only give it 10%, but over time you understand which is the better of the models and sort of traffic shift based on that. And this needn't be one time, right? Like what you want to have is a mechanism to collect this data, constantly monitor, and then change that. And it's actually pretty easy to do this in Lambda. As you can see, we just need to update alias and change the routing config to get or change the percentages. Currently, we're restricted to just 2 models, but I thought it'd be good to sort of show the general idea in terms of what you want to do with more sophisticated deployment here. We're almost at the end, so I wanted to get some take-home messages out there. When your access patterns are not uniform, they're spiky or bursty, serverless will be much better than your traditional ways of deployment. It's nice to not manage servers when you don't need to. It's not that every application, this makes sense, but do consider when servers are more meaningful. Event-driven data architectures fit really nicely. Like as you've seen through those applications that people have built, it's easy to translate, to manage, and actually build other applications, more generic applications on top. And the good thing about this paradigm is you have control over the code and the execution units. It's a great alternative for latency-insensitive applications, especially in the area of machine learning for predictions, as we saw with those benchmarks. Like totally viable to use AWS Lambda here. And what I would urge is, if not just for standalone applications, consider using this as the connective tissue for communicating between your cloud applications. Here are some GitHub resources that you can find those projects that I mentioned in. I wanted to get time, open up for questions before I leave. Thank you.